All right, so this is going to be an interesting one. At some point here, we're going to draw a picture together. Normally, I would do that on the board. I'm going to try it in the paint program. I already started, and my drawing is bad to begin with, but in paint, it's probably going to be even worse, but we'll give it a shot here. All right, so this is the plate tectonics follow-up to continental drift that we were talking about last time. Again, continental drift was a theory that said that in the past, the continents were located in a different spot. When asked how that could happen, Wegener did come up with some ideas about how these continents might move, but all of those were quickly ruled out, and scientists found that those kinds of things are not possible to happen. So plate tectonics is a theory that came along much later, and that's what differentiates it from continental drift. Plate tectonics describes how it is that plates move. So before we get to that, just a quick aside on how lava lamps work. So you've probably seen lava lamps before. They have these two fluids in them. There's a light bulb that produces heat at the bottom. And we have one fluid that's a different density than the other one. So as that, in this case, yellow material heats up, because it's closer to the heat source, the light, it moves towards the top of the lava lamp. It cools, becomes a little bit more dense, and sinks back down. And creates this convection current. Okay, so that's an important aspect. These convection currents, they happen in boiling water, they happen in the atmosphere. We will talk about convection currents throughout the course in a couple of different ways, but it's a important phenomenon based on density differences that arise due to temperature differences. Okay, so we've got to understand what a convection current is in order to understand what's causing the plates to move. Again, this kind of says what I've said earlier, the difference between continental and plate tectonics. So plate tectonics was somewhat discovered when they weren't looking for it. It was a serendipitous discovery. And so basically searching the ocean floor in times of war, looking for tethered bombs and things of that nature. You developed sonar. They used the sonar to map the ocean floor, and they discovered what we call the mid-ocean ridge, which is abbreviated MOR, which is essentially a large underwater mountain chain. Looks a little bit like this. It snakes through the ocean, all the oceans around the globe. It's the largest mountain chain on our planet. Most of it is beneath the surface. It does stick up in a few spots here, you can see in Iceland. I'll let Bill tell you a little bit more about the mid-ocean ridge. All right, so the idea of the mid-ocean ridge is it is a mountain chain, but it also is a place where magma comes out. So it's more of an underwater volcano that extends for quite a long distance, about 12,000 miles. Again, most of it's undersea. It does stick out of the water in a few spots. All right, so here's a map, and they vary somewhat depending on the size of the plates that you want to count. But the idea is that it's not a continent that's moving, it's a lithospheric plate. All right, so you've probably heard about the layers of the Earth in terms of the crust, the mantle, the inner core, the outer core. There's two other sort of operational layers that we're going to talk about today. One is the lithosphere, and the other is the asthenosphere, and we'll see those in the drawing that we're going to make. The lithosphere is the top layer. It is essentially the crust. Right? It's actually the crust and a little bit of the mantle, but for all intents and purposes, when we talk about lithospheric plates, we're talking about the crust. When we're talking about the asthenosphere, it's a layer of the mantle, not the entire mantle, but a layer of the mantle. So here we have the plates made of lithosphere. And that lithosphere contains, in most cases, a little bit of continental crust and a little bit of oceanic crust. Okay, so oceanic crust here in yellow, and the continental crust, the purplish color outlining the continents. Most of them are named pretty aptly for the region. Eurasian plate contains Europe. The Pacific plate is the Pacific Ocean. North American plate contains North America. The thing to think about here is that these plates are like these annoying puzzles that I can never seem to solve. If you move one piece, all of the other pieces move, right? So if one of these plates is moving, they're moving in different directions. We kind of saw that when we looked at continental drift and the speed at which they're moving. So it's very dynamic. They're all moving either towards one another, convergent plate boundaries, away from one another as divergent plate boundaries, or in the case of the Juan de Fuca plate here and the North American plate, they are transform faults. That's the San Andreas fault right there. All right, so how do we know where the plate boundaries are? This map kind of shows it pretty well. If we look at the location of volcanoes and earthquakes and basically connect the dots and triangles, we get a pretty good line that outlines each of the plates. All right, so that's one way. That, in addition to being able to see fault zones, being able to see those mid-ocean ridge features as well, as you can see it's on here. All right, so I'm going to jump over to paint here. I started to draw a picture. Like most of my pictures, I have to tell you what you're looking at. So here we have the ocean floor, which is oceanic crust. Over here we have continental crust. I've mirrored it on both sides. Above that we have the water line, and there's a little boat. Here's my attempt at a house. So here's the lithosphere, which we would call oceanic crust or continental crust. And that's a cooler temperature closer to the surface. Beneath that is the asthenosphere, which is a hotter temperature. Okay. All right, so within the asthenosphere then we have warm material that is rising. As it rises, it cools, and it sinks back down to create these convection currents. The direction of these arrows is important. Whoops. In this case, they are going in opposite directions, and that's important because what that does is it's forcing magma up through this mid-ocean ridge. So this is our mid-ocean ridge right here. It's a ridge. In fact, it kind of is shaped more like that, which is why it's called a ridge. I'm having a hard time drawing, but something like that. So it's called a ridge. So this magma is coming out, and as it turns out, about half of it goes to the right, and about half of it goes to the left, which means that these sides are really mirroring one another. The right side is almost identical to the left side. Right? So what that means is if you go, let's say, 100 miles to the right, 100 miles to the left, the rock that is cooling there is about the same age, if we date it. Okay, so this magma cools out and it forms new igneous rock. Really, it's forming mostly basalt, the ocean floor. Okay, so as we move away from the mid-ocean ridge, the age increases as we move away. The rocks get older and older and older as we move away from the mid-ocean ridge. Okay. All right, so that's sort of seafloor spreading. But what's happening, so the driving mechanism, there are two. The first one illustrated here are these convection currents in the asthenosphere. Right? These convection currents in the asthenosphere move the oceanic crust away from the mid-ocean ridge. It's a divergent plate boundary. Okay, so this think of this convection current as a so this is similar to a conveyor belt, and the oceanic crust is a package on it. So that conveyor belt is just spinning around and around and around. It doesn't really go anywhere, but the oceanic crust, the package on top, is what's moving. Right, and so that's moving away from the mid-ocean ridge. So it can only go so far, and it comes in contact with the continental crust. The oceanic crust is more dense than the continental crust, so when these two hit, they don't hit head-on. There's a convergent plate boundary. And there's three types of convergent plate boundaries, right? There's continental crust can collide with continental crust, oceanic crust with oceanic crust, or oceanic crust with continental crust, which is happening here. Because they're different densities, in this case, the oceanic crust, which is more dense, is pushed underneath of the continental crust. Okay. The more dense material hits and is pushed underneath because it's more dense. Okay. Then at that point, the second mechanism that causes plates to move is occurring here. This is called slab pull. Right? You can illustrate this by taking a sheet of paper and pushing it off a desk so that maybe a quarter of it's hanging off the desk, and you keep pushing it till maybe a third's hanging off the desk, and then the the weight of the paper is going to pull the rest of the sheet off the disk. So that's kind of what's happening here. The sheer mass of rock here is pulling the rest of this slab with it down into the asthenosphere. But once it gets into the asthenosphere, change my color again, then what's going to start happening is this is going to start melting. If I can write that. It's going to start melting. That's horrible. So some of that will melt, and then it will just become part of the asthenosphere. Some of that melting is going to form blobs that come up to the surface to form a volcano, right? So we have a volcano here that is the result of an oceanic crust melting as it collides with a continental crust. Okay, so there's two main things that's happening here. Again, we have the convection current in the asthenosphere that's causing the oceanic crust to move apart. And then we have the slab pull that is occurring as the oceanic crust is pulling the rest of it at this zone here that's called a subduction zone. All right. So to jump back to the PowerPoint, that's all shown in this picture. Maybe a little bit better. We have our mid-ocean ridge. We have the plates moving away from the mid-ocean ridge to the point that they collide with continental crust. It's pushed underneath, it remelts. Some of it moves to the surface to form magma, volcano. Okay. There's some other features that are going on here, island arcs, and different things like oceanic crust collides with oceanic crust, but I'm not going to focus on that. Right now I'm focusing on the mid-ocean ridge and the subduction zone. Okay, so these convection currents are what's driving that. This is a good video. It shows that in a much better animation than what I can draw, so I encourage you to give that a watch. And this is just a reminder that while we're looking at one part of this, say like this little image right here, really this is happening around the globe. There are multiple cells like this where this is happening. All right, so here we see what I was saying earlier. As you move away from the mid-ocean ridge, you can see here's the ridge. We go to the right, we go to the left. It's the same age, basically mirrored as you go both directions away from the mid-ocean ridge. All right, so the other thing that they noticed with the mid-ocean ridge is this is a second way to determine the age of, or the rate of plate movement and the direction. So we know the direction because they're moving away from the plate. But the other thing that happens here that's illustrated here is as this magma cools, the iron-rich minerals in it align themselves towards magnetic north pole. But over time, there have been reversals in the poles so that a compass would point not north but south. So these magnetic reversals are locked into the crust, and we see there's these bands that alternate. We also see it in volcanoes. So here we have the pluses and minuses that show these changes in direction as you move away from the mid-ocean ridge. So we would have the age of these, and we have the distance that they are apart, and we can use that to calculate the speed at which plates move. And I do have an activity for that, but I'm going to skip it for now for this class. Okay, so there's two ways to measure the speed at which plates move. We looked at hotspot volcanoes, and the second way is to use these magnetic reversals in the mid-ocean ridge. All right, so a quick question to think about. When we think about the rocks on the ocean floor, they are much, much older than continental crust. I'm sorry, much younger than continental crust. Continental crust being about 4 billion years old. The ocean floor being only about 150 million years old. So think about why that is, and we can discuss that on Tuesday when I see you in the Blackboard Collaborate Ultra meeting. All right, see you then. Bye.